The National Electrical Code, or NEC, addresses the issue of running control wiring and motor wiring in the same conduit in section 725.136b. It is generally allowed to run 24 volts DC control wiring and 480 volts alternating current motor wiring in the same conduit, provided certain conditions are met. Firstly, the conduit must be a metallic raceway such as electrical metallic tubing, rigid metal conduit, or intermediate metal conduit. This provides a grounded enclosure. Secondly, the control wiring and motor wiring should be isolated from each other within the conduit by means of a physical barrier, for example, a separate partition or divider. Thirdly, the control wiring must be rated for the same voltage as the motor wiring, that is, 480 volts alternating current. The exception to this rule is if the control wiring is a Class 2 circuit. Class 2 circuits are low-energy circuits that meet specific criteria, such as having a maximum voltage of 60 volts DC or 150 volts alternating current and a maximum power of 100 volt amps. In this case, Class 2 control wiring is permitted to be run in the same conduit as motor wiring without the need for isolation. The NEC allows this arrangement because firstly, the grounded metallic raceway provides a protective barrier between the control wiring and the motor wiring. Secondly, the physical barrier further prevents contact between the two types of wiring. Thirdly, rating the control wiring for the same voltage as the motor wiring ensures that it can withstand any potential surges or transients. While the NEC allows it, it is generally good practice to separate control wiring and motor wiring into different conduits whenever possible to minimize the risk of interference or damage. Let's delve deeper into the specifics of NEC section 725.136b. This section provides the guidelines for the separation of Class 1, Class 2, and Class 3 circuits. It's important to understand that the requirements differ based on the class of circuit. For Class 1 circuits, which often include control wiring operating at higher voltages, the NEC mandates specific separation methods when run in the same enclosure or raceway as power conductors. These methods include physical barriers or suitable insulation rated for the highest voltage present. Class 2 and Class 3 circuits, being low energy, have more relaxed requirements. However, even with these circuits, it's crucial to adhere to the NEC guidelines to prevent unintended interactions and ensure safety. Now let's consider the metallic raceway requirement in more detail. The purpose of using a metallic conduit such as ENT, RMC, or INC is to provide a grounded, electrically continuous enclosure. This grounded enclosure serves several crucial functions. Firstly, it provides a low impedance path for fault currents, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly clear a fault to minimize the risk of electrical shock or fire. Secondly, the metallic conduit shields the conductors from external electromagnetic interference or EMI, which can disrupt sensitive electronic equipment. Thirdly, it provides physical protection to the conductors, safeguarding them from damage caused by mechanical stress, moisture, or other environmental factors. When installing conductors in metallic raceways, it's important to follow proper grounding and bonding techniques to ensure the effectiveness of the grounded enclosure. This includes using appropriate fittings and connectors, as well as bonding bushings or jumpers when necessary, to maintain electrical continuity throughout the raceway system. The physical barrier requirement is another critical aspect of safely running control and motor wiring in the same conduit. The barrier serves to prevent direct contact between the conductors, which could lead to insulation breakdown, short circuits, or other hazardous conditions. The barrier can take various forms, such as a dedicated partition within the conduit, a non-metallic divider, or even the use of separate inducts or raceways within the main conduit. When selecting a physical barrier, it's important to choose a material that is compatible with the environmental conditions and that is rated for the voltage and temperature requirements of the conductors. The barrier should also be securely installed to prevent it from shifting or dislodging over time. The requirement for control wiring to be rated for the same voltage as the motor wiring is often overlooked but is essential for safety. Even though the control wiring may operate at a low voltage under normal conditions, it must be able to withstand the full voltage of the motor circuit in the event of a fault or transient voltage surge. Using control wiring with an appropriate voltage rating ensures that the insulation will not break down under high voltage conditions, preventing short circuits and other hazardous events. It's also important to select control wiring with an appropriate ampacity or current carrying capacity for the intended application. The ampacity of the wire should be sufficient to handle the maximum current that the control circuit will draw, taking into account any directing factors for ambient temperature or conductor bundling. Now let's focus on Class 2 circuits. Class 2 circuits are defined by the NEC as low-energy circuits with specific limitations on voltage and power. These limitations are designed to minimize the risk of electrical shock and fire. To qualify as a Class 2 circuit, the voltage must not exceed 60 volts DC or 150 volts alternating current, and the power must not exceed 100 volt amps. These limitations are typically achieved by using power supplies or transformers that are specifically designed to meet Class 2 requirements. Class 2 circuits are commonly used for low-voltage control applications such as powering sensors, switches, and other devices. Because of their low-energy nature, Class 2 circuits are generally considered to be safer than Class 1 circuits and have less stringent wiring requirements. However, it's still important to follow the NEC guidelines for Class 2 circuits to ensure safety and prevent unintended interactions with other circuits. When running Class 2 control wiring in the same conduit as motor wiring, the NEC permits this without the need for a physical barrier, provided that the Class 2 circuit meets the voltage and power limitations. This exception is based on the assumption that the low-energy nature of the Class 2 circuit poses a minimal risk of electrical shock or fire, even if the insulation were to fail. However, it's still recommended to maintain separation between Class 2 and motor wiring whenever possible to minimize the risk of interference or damage. Beyond the specific NEC requirements, there are several other factors to consider when running control and motor wiring in the same conduit. Firstly, it's important to consider the potential for electromagnetic interference or EMI between the control and motor circuits. Motor circuits can generate significant EMI, which can disrupt the operation of sensitive electronic equipment connected to the control circuits. To minimize EMI, it's recommended to use shielded control cables and to ground the shields properly. It's also helpful to physically separate the control and motor wiring as much as possible within the conduit. Secondly, it's important to consider the potential for voltage transients or surges on the motor circuit to damage the control equipment. Voltage transients can occur due to switching operations, lightning strikes, or other events. To protect the control equipment from voltage transients, it's recommended to use surge suppressors or transient voltage surge suppressors, or TVSS, on both the control and motor circuits. Thirdly, it's important to consider the potential for heat buildup within the conduit, especially when running multiple conductors at high current levels. Heat can degrade the insulation of the conductors and reduce their ampacity. To minimize heat buildup, it's recommended to follow the NEC guidelines for conductor fill and to use conductors with a higher temperature rating. Finally, it's important to consider the long-term reliability and maintainability of the wiring system. Running control and motor wiring in separate conduits can make it easier to troubleshoot and repair problems in the future. It also reduces the risk of accidental damage to one circuit while working on another. While the NEC permits running control and motor wiring in the same conduit under certain conditions, it's generally a good practice to separate them whenever possible to minimize the risk of interference, damage, and safety hazards. Let's discuss some additional best practices for running control and motor wiring, regardless of whether they are in the same conduit or separate conduits. Proper labeling and identification of conductors is crucial for safety and ease of maintenance. Clearly label each conductor at both ends with its function and voltage rating. Use different colored wires for different types of circuits, following the NEC color coding guidelines. Use wire markers or tags that are durable and resistant to fading or abrasion. Proper support and securing of conductors is also essential to prevent strain on connections and to maintain the integrity of the wiring system. Support conductors at regular intervals using appropriate cable ties, clamps, or straps. Avoid over-tightening cable ties, which can damage the insulation of the conductors. Ensure that conductors are properly protected from physical damage, such as abrasion or crushing. Proper termination of conductors is also critical for reliable and safe operation. Use appropriate connectors and terminals that are rated for the size and type of conductor. Tighten connections to the proper torque specification using a calibrated torque wrench. Inspect connections regularly for signs of corrosion, looseness, or damage. Proper grounding and bonding of equipment is essential for safety and to minimize the risk of electrical shock. Ground all metallic enclosures, raceways, and equipment using appropriate grounding conductors and connectors. Bond all non-current carrying metallic parts together to create a low impedance ground path. Test the grounding system regularly to ensure that it is functioning properly. Proper overcurrent protection is also critical to protect conductors and equipment from damage due to overloads or short circuits. Use circuit breakers or fuses with the appropriate ampacity rating for the conductors and equipment being protected. Coordinate the overcurrent protection devices to ensure that they trip in the correct sequence in the event of a fault. Test the overcurrent protection devices regularly to ensure that they are functioning properly. Proper installation and maintenance of control and motor wiring is essential for the safety and reliability of electrical systems. By following the NEC guidelines and best practices, you can minimize the risk of electrical hazards and ensure the long-term performance of your equipment. Remember that the NEC is a minimum standard, and in some cases, it may be necessary to exceed the NEC requirements to meet the specific needs of your application. Always consult with a qualified electrical engineer or electrician to ensure that your wiring system is safe, reliable, and compliant with all applicable codes and standards. In addition to the technical aspects of running control and motor wiring, it's also important to consider the human factors involved. Proper training and education of electrical workers is essential to ensure that they understand the hazards of electricity and how to work safely. Provide regular safety training to all electrical workers, covering topics such as lockout-tagout procedures, personal protective equipment, and arc flash safety. Encourage electrical workers to report any safety concerns or hazards that they identify. Foster a culture of safety in the workplace, where safety is valued above all else. By addressing both the technical and human factors, you can create a safer and more reliable electrical system. Let's explore some specific scenarios where running control and motor wiring in the same conduit might be considered, and the additional precautions that may be necessary. In industrial automation systems, it is common to have numerous sensors, actuators, and control devices that need to be connected to a programmable logic controller, or PLC. These devices often require both power and control signals. Running the power and control wiring in the same conduit can simplify the installation and reduce the amount of conduit required. However, it is important to carefully consider the potential for electromagnetic interference, or EMI, in these applications. Use shielded control cables and proper grounding techniques to minimize EMI. In motor control centers, or MCCs, it is common to run the control wiring for the motor starters in the same conduit as the power wiring to the motors. This can simplify the wiring and reduce the size of the MCC. However, it is important to ensure that the control wiring is properly rated for the voltage and current of the motor circuit and that the control wiring is protected from overloads and short circuits. In hazardous locations, where explosive gases or dust may be present, it is essential to follow the NEC requirements for wiring in hazardous locations. These requirements may include the use of explosion-proof conduit, fittings, and enclosures. It is also important to ensure that all electrical equipment is properly rated for the hazardous location. In these applications, it may be necessary to run control and motor wiring in separate conduits to minimize the risk of ignition. When retrofitting existing electrical systems, it may be necessary to run control and motor wiring in the same conduit due to space limitations or other constraints. In these cases, it is important to carefully evaluate the existing wiring system and to ensure that it is in good condition and that it meets all applicable codes and standards. It may also be necessary to upgrade the existing wiring system to meet the current NEC requirements. In summary, running control and motor wiring in the same conduit is permitted by the NEC under certain conditions. However, it is important to carefully consider the potential hazards and to take appropriate precautions to minimize the risk of electrical shock, fire, and equipment damage. Always consult with a qualified electrical engineer or electrician to ensure that your wiring system is safe, reliable, and compliant with all applicable codes and standards. Remember, safety is always the top priority when working with electricity. Take the time to properly plan and install your wiring system, and never take shortcuts that could compromise safety. By following the NEC guidelines and best practices, you can create a safe and reliable electrical system that will provide years of trouble-free operation. It is also important to stay up to date on the latest changes to the NEC. The NEC is revised every 3 years, and there may be changes that affect your wiring system. Subscribe to electrical trade publications and attend electrical industry conferences to stay informed about the latest developments in the electrical industry. Consider the impact of harmonics on your wiring system. Harmonics are distortions of the voltage and current waveforms that can be generated by nonlinear loads such as electronic ballasts and variable frequency drives. Harmonics can cause overheating of conductors and equipment, as well as interference with sensitive electronic equipment. To mitigate the effects of harmonics, it may be necessary to use harmonic filters or to oversize conductors and equipment. Ensure proper coordination of overcurrent protection devices. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from damage due to overloads and short circuits. It is important to properly coordinate the overcurrent protection devices to ensure that they trip in the correct sequence in the event of a fault. This will minimize the amount of equipment that is affected by the fault and will reduce the risk of damage. Consider the impact of voltage drop on your wiring system. Voltage drop is the decrease in voltage that occurs along the conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or to operate inefficiently. To minimize voltage drop, it is important to use conductors of the appropriate size and to keep the length of the conductors as short as possible. Consider the use of energy-efficient wiring methods. There are a number of energy-efficient wiring methods that can help to reduce energy consumption and save money. These methods include using conductors with a low resistance, using lighting control systems, and using energy-efficient transformers. Be aware of the potential for arc flash hazards. Arc flash is a dangerous electrical explosion that can occur when there is a fault in an electrical system. Arc flash can cause serious burns, injuries, and even death. To protect against arc flash hazards, it is important to wear appropriate personal protective equipment, or PPE, and to follow safe work practices. Conduct an arc flash hazard analysis to determine the potential arc flash hazard levels in your electrical system. Implement an arc flash safety program to train employees on arc flash hazards and safe work practices. Keep accurate records of your wiring system. It is important to keep accurate records of your wiring system, including wiring diagrams, equipment specifications, and maintenance records. This information will be helpful for troubleshooting problems and for making future modifications to the wiring system. Inspect your wiring system regularly. It is important to inspect your wiring system regularly for signs of damage, wear, or corrosion. Replace any damaged or worn components promptly to prevent electrical hazards. Test your wiring system regularly. It is important to test your wiring system regularly to ensure that it is functioning properly. This includes testing the grounding system, the overcurrent protection devices, and the insulation resistance of the conductors. By following these additional guidelines, you can create a safer, more reliable, and more efficient electrical system.